Sweet. Um, Common mode rejection. Does anyone know what does that mean? Has anyone heard of this terminology, common mode rejection? So we'll try
Common
to.
mode,
Uh-huh.
a signal that's the same polarity in both directions.
So close. Basically, you have something common in the two signals. Okay. So remember, in a operational amplifier, you got two terminals, right? This is your um, non-inverting terminal, you got inverting terminal. Okay, you may have some kind of signal connected to these two terminals, and they may have something in common. Does anyone guess what is something that could be common to both of these signals? What could be a source of that signal? Okay, that common source is basically noise. Okay, and it could be few other things. So uh, common mode rejection ratio, also referred to as CMRR, this basically exists in differential amplifier that we did last week. So when you have a PCB board and you have a circuit on it, it is operated in high electromagnetic field. In that case, the electromagnetic interference, which is coupled to the circuit, is also common to both terminals. Okay, so this is one common source of the common mode input signal. So if say you have some input signal, and that input signal is connected to one of the terminals of the op-amp. Not all of it is basically signal. Some of it could be noise, and that could be from the electromagnetic interference. Similarly, if you have another input signal over here, okay, not all of it is that input signal that may be coming from a sensor. So say this may be sensor 1 and this may be sensor 2. Some of it could be noise. Okay, so what differential amplifier, what does it do? Differential amplifier, remember, differential amplifier basically takes the difference of the two voltages at the input and then amplified by R2 over R1, right? So if this contains some kind of noise, so that means noise is also going to be amplified, right? And we don't want that. So there's a phenomena called common mode rejection ratio, which basically is a blocker to this noise or unwanted signal. Okay, and we'll see how that thing is worked and how it is calculated. Okay, so the op-amp common mode rejection ratio is the ratio of the common mode gain to the differential mode gain. In electronics, the common mode rejection ratio of a differential amplifier is a metric used to quantify the ability of the device to reject common mode signals and those that appear simultaneously and in phase on the both inputs. Okay, now imagine that you have an amplifier and it's connected to a signal which is common to both the terminals, that like you see on the left. Okay, and I'm going to say the output voltage is VOCM. Basically, it's a common mode output voltage. So VCM here is your common mode input signal or voltage. And similarly, VOCM is the common mode output signal or voltage. Okay, this differential amplifier will have some kind of gain, and we will call it ACM, common mode gain. So if I am trying to calculate the output, common mode output voltage here, VOCM, we know that this is going to be equal to ACM dot, uh, say, VD, which is the differential voltage over here, okay? VD, or in the previous lectures, we have said VN, same thing. I'm just saying VD here, differential voltage. Okay, now, in this case, if VCM is fed to both the terminals, plus and minus, that would mean the differential voltage is going to be what? VD. Yes, folks. What did we learn here? That differential voltage or the input voltage is equals to VP minus VN, correct? Okay, this is your VP, positive terminal, and this is your VN, negative terminal. Because you have VCM connected to both VP and VN, therefore, what does that mean? VP will equals to VN. And if that's the case, what would be your differential voltage, VD, then?
0.
0, okay? And if this is 0, then VOCM will be what?
0.
0, right? So this whole term will become 0, and that happens when two input terminals are tied together, okay? So that's the ideal situation, okay? That's the ideal situation. But in reality, that's not going to happen. This number is not going to be 0, okay? This number is going to be very, very small, very, very small, close to 0, okay? All right, so ACM, which is the common mode gain, from this equation here, I can derive it's going to be a ratio of VOCM and VCM, okay, where VCM is the common mode input signal and the VOCM is the output uh, input signal. And this is going to be less than 1 always, okay? So your VOCM is going to be, because VOCM is very, very small and VOCM is going to be bigger, so it's always going to be less than 1, okay? Now also, let's come to the graphic on the right hand side. So say I have positive terminal which is connected to some input signal, and then also I have another input signal here, okay? And I say this is V2, this is V1, okay? The potential difference between these two signals, it's say VD, okay? This has some gain, differential gain A, this amplifier. So what is the output equation here? Can anybody tell me what is going to be the output voltage equation? Yes, folks.
A times VD.
Okay, AD times VD, that is correct. And if I want to, I can also rewrite this equation in this form where VD is basically V1 minus V2, correct? This is VD is the difference between the two, positive, which is V1, minus this negative terminal, which is V2, okay? Same thing basically. How do we calculate this CMRR? Well, if we know these two parameters over here, we can calculate the common mode rejection ratio, this right here. These two are, if known, we can find out the common mode rejection ratio. And what is the relationship between these two parameters? Well, your CMRR, common mode rejection ratio, is equals to AD, differential gain, over common mode gain, okay? How do you get a differential gain? Well, we get it from here, and ACM, we get it from here, correct? Okay, also, this is usually expressed in decibel, so the equation becomes CMRR equals to 20 log of base 10 of AD over ACM, and that gives you in decibel, okay? And therefore, your output voltage, the final output voltage, is going to be the sum of AD dot VD, which is this thing right here, okay, plus ACM dot VD, okay, ACM dot VD. Remember this right here is coming from the common mode signal, and the goal of the common mode rejection ratio, ideally you want this number to be as small as possible, okay? And we'll do a couple of examples later on, and you'll get the idea. What does this mean? So right now we have everything in expression format, and then we can take it from here and then work upon it. But I want you to understand that this equation right here, once we calculate this number is going to tell us what is an ability of the device, in this case operational amplifier, to reject a common signal and allow the signal to go past if the two inputs are not same, okay? Op-amp ideally should be able to suppress this common mode signal, which in this equation is this term right here, okay? All right, let's move forward. This was pure basics here. Is everybody following me so far? All set?
Yeah.
Okay, all right, let's go here now. Okay, we have been given a task, calculate the common mode rejection ratio for the circuit shown below. Okay, this circuit is not complete, so we're gonna complete it first. Okay, so say to the inverting terminal, which is a negative terminal, I'm going to connect a source, and say this is negative 0.5 millivolt. Okay, we know that this is going to be Vn, right? We know that this is going to be Vp. Okay, and this Vp, which is the non-inverting terminal, is also connected to an input signal, which is 0.5 millivolt. Okay, all right. We know that we have this positive VCC and negative VCC here, and then V naught is basically given here. It's going to be 8 volts. Okay. Now from this circuit, we know, is Vp and Vn equals to Vn or not? Is Vp equals to Vn here or not? Question. Say it again.
The absolute values are the same.
Yeah, but if you look at the magnitude of it, it's not the same, right? So you got negative 0.5 millivolt here and you got 0.5 millivolt here. So Vp is basically not equal to Vn. The differential voltage, which is the difference of these two voltages, that equals to Vp minus Vn, correct? Vp here is how much? 0.5 millivolt minus, then we have Vn. Vn is negative 0.5 millivolt here. Okay, so if I do the math here, I basically get 0.5 millivolt plus 0.5 millivolt, and that gives me the differential voltage of 1 millivolt. Okay, we know the equation for differential gain is A of t equals to V naught over Vd. Okay, V naught is 8 volts here, correct? V naught is 8 volts. So if I put 8 volts here, and then this is Vd is 1 millivolt, which I get from here, correct? Volts and volts will cancel out, and this would give me a gain of 8,000, correct? And we will box it so we can use this later on. Okay, now let's move to this circuit over here. Again, this is going to have some positive VCC here, negative VCC here. Same circuit like which I had over here. Same circuit. This is pretty much same. Actually, it is the same. It's just like I have split it into two because I wanted to do the analysis for the differential gain separately and then for the common mode gain separately. So here is what is going as a common mode signal to this. Let's work it out. So I have the positive terminal, I have one input signal, which is again basically VCM. Okay, VCM, common mode signal, and this is 1 millivolt. Okay, again, I have common mode signal here, same VCM, and this is also 1 millivolt here. Okay, remember you have your VP here, you have your Vn here. This is going to be your VOCM, output voltage, common mode output voltage here. In this case, if I can just draw a line here. Here, I have Vp equals to Vn, and they are both 1 millivolt, correct? 1 millivolt here, 1 millivolt here. Okay. What should be V naught ideally here? If I may ask this question, same question again. Ideally, V naught is going to be what? If Vp, Vn are same, right?
0.
Which means 0, which means V and Vp is equal to Vp minus Vn, both are same, so that is 0. If Vn is 0, that means V out is going to be 0, ideally, but like I said, there are some imperfection in op-amps. It's going to be very, very tiny voltage close to 0, and that is given in this question as 12 millivolt. Okay, so your VOCM uh, is basically 12 millivolt. Now, if I am going to find out the common mode gain, which is a ratio of common mode output voltage over common mode input voltage. So VOCM is 12 millivolt, 12 millivolt. VCM is 1 millivolt, right? VCM is 1 millivolt. Millivolt and millivolt will cancel out, right? So I get the gain of 12. Okay. Now I have to find out common mode rejection. There should be one common. I can also change the color here too. Okay, yeah, so common mode rejection ratio, and we know it is a ratio of AD differential gain over common mode gain. Differential gain was how much? 8,000. 8,000. ACM was 12. Okay, ACM was 12. Okay, so if I do the math, I basically get 666.67. We would like to convert this into decibel because that's how they are rated. So in decibel, basically taking a 20 log with base 10 of this number 666.67, and that would equal to 56.48 decibel. Okay, so this is important to know, and later on I'll show you a slide where I would show you like what this number corresponds to in terms of the frequency or the noise, and then the common mode signal. Okay, so what we learn here is basically what is going to be the output voltage here. The output voltage here is going to be this right here, which was 8 volts plus 12 millivolt. 12 millivolt. Okay, this is going to be your total output voltage, where this is the output voltage, the differential voltage, which is magnified, and this is basically the common mode. It will not completely like 100% eliminate, but it will get to very close to zero. And if you look at it, 12 millivolt is basically 0.012 volts, right? So it's a very, very small number. Okay, so the higher this number, the higher this number, the smaller this is going to be. Okay. Okay. All right. Let's move on to another example, and this is again interesting. Okay, so you have another amplifier, and what I'm gonna do is I'm going to connect this to a resistor. Take a resistor right here, and then connect to the negative terminal. And then there would be a feedback like this, and it's connected to the output voltage. Okay, I'm gonna say this is R2. The value of the R2 is 10 kilo ohms. Okay, this is R1 right here, and R1 is 1 kilo ohm. Okay, I'll say this is my V1, some input signal over here. Okay, to the positive terminal, we would have say another input signal which is connected to resistor. Okay, and then it's connected to this, and then here I have another resistor, and this is a voltage divider configuration, by the way. Okay, so this is R2. R2 is 10 kilo ohms. Okay, you have R1 here, which is 1 kilo ohm, and then this is V2. Okay, also this is 50 hertz. Okay, this is also V2 is also 50 hertz. Okay, the magnitude is 2 millivolts. Maybe I can change the color here. So this is going to be 2 millivolts here, and then this V2 is also 2 millivolt here. Okay, there are few more things that are given in this circuit, and those are that CMRR, common mode rejection ratio, is given here, okay, and that is equal to 90 decibel, okay. VD, which is the potential difference between these two circuits, VD, okay, that is equals to 5 millivolt at 1 kilohertz, okay. This is basically the peak value, okay, the peak value, okay. All right. What do we need to do in this circuit? Well, our goal is to find out how well this op-amp is able to suppress the common mode signal. Okay, if I ask you guys what is the amplitude of the common mode signal, how much is that? Yes, folks, it is 2 millivolt, right? It's 2 millivolt over here. Okay, all right. So let's start the analysis, okay? And I'm going to start off with the equation for the output voltage. We know that the output voltage is equals to AD dot VD, okay? Now, this is a differential amplifier over here. And I told you guys earlier at the beginning that common mode rejection ratio is a phenomena that is associated with differential amplifier. Differential amplifier. And can anybody tell me, and I actually wrote it in the previous on the previous page, what is the equation for V naught for differential amplifier? Yes, folks. Anybody remember that from last week? Okay, so it is going to be V naught equals to gain times differential voltage. And what is this AD gain here? It's actually R2 over R1, okay? Times differential voltage, basically that will be V2 minus V1, okay? So differential, as the name suggests, you know, it's gonna take the difference of the two input signal and then amplify it. So this is sort of your beta factor, right? Beta factor is R2 over R1. So if you want to amplify it by 1,000 times, you can choose the value of R2 to be 1K and then R1 to be 1 ohm. So your output voltage will be the difference of the two input voltages, and then it will be amplified 1,000 times, correct? So it's important to remember this equation because we will be using this equation here. So AD is what? R2 over R1. R2 over R1, okay? And then VD, which is differential voltage, is VP minus VN. This is VP and this is VN. VP is basically V2 and VN is going to be V1 basically because it's directly connected to V1. So I basically get V2 minus V1, okay? All right. Now here, what is the value of R2 and R1? R2 is 10 kilo ohms and R1 is 1 kilo ohms, correct? So let's put the values in here. 10K over 1K, okay? V2 minus V1, the differential voltage is given. The differential voltage is given here, and that is equivalent to 5 millivolts. Okay, so I get 5 millivolts here. This K and this K will cancel out, and if I do the math here, I basically get V naught equals to 50 millivolts. Okay, so I'm gonna box this so I may need that later on. Okay, now how do you calculate CMRR? What is the equation for that? Well, our CMRR, okay, which is also given in this question, is equivalent to 90 decibel, okay? It's equivalent to 90 decibel, okay? And I can also write it down as 20 log with base 10 AD over ACM, correct? Okay. I'm gonna switch things around here such that, you know, I'm gonna take this 20 over here. So 90 divided by 20 is going to give me 4.5 equals to log 10 of AD over ACM. And I can also rewrite this equation as AD over ACM equals to 10 to the power 4.5. okay? Um, and that would give me, this number is equivalent to 31623, okay, approximately this number, okay? We also know, let me go over here. We also know that ACM, the common mode gain, equals to, because this was CMRR, okay? From this equation over here, I can drive the value for ACM, which is going to be AD over CMRR, correct? So AD is how much? AD is, AD was this number, right? R2 over R1. So AD is R2 over R1. R2 is 10K. R1 is 1K. So KK will cancel out. So you get 10 here. So AD is 10. So I get 10 here. And then CMRR is basically equals to this number that we got here, correct? So I will have 31623 here, okay? And then what is my common mode output voltage? Well, that is a product of ACM, common mode gain, times VCM, common mode voltage. So here, ACM, I'm gonna just put this whole value for ACM over here. 10 divided by 31623, okay, times VCM. VCM is how much? VCM is 2 millivolt, right? So VCM equals to 2 millivolt, which is the common to both the input signal. Okay, I can think of it as a noise or, you know, some kind of distortion in the signal. So that is going to be 2 millivolt. So if you do the math here, you'll get your output, common mode output voltage to be equal to 0.63 microvolts. 0.63 microvolt. That is insanely a small number. If I can write it down, if I can write in volts, that would be how much? 0.000345663 volts. Okay. So is this a good number or not? Question.
Yes, that's a good number.
It's a good number because initially, if you look at it, it was how much? Initially, it was 2 millivolt. And this magic device is able to cut down that number to such a small number over here. So that's actually job well done. So if I ask you what is the total voltage is going to be, the total voltage is going to be, what did we get? 50 millivolt here, correct? VO, 50 millivolt, 50 millivolt plus this VOCM, which is plus 0.63 microvolt. Okay, so it's a very, very tiny number. If you add that, you will basically get this, you know, the output voltage right here. So common mode rejection ratio are very, very important and critical parameter of any operational amplifier, and usually we, you know, think of them when we are working with the differential amplifiers. I told you I'm going to give you a relationship between the common mode rejection ratio. So here you have common mode rejection ratio here. And then you have on the x-axis frequency. And what relationship do you see over here? As the frequency is increasing, the common mode rejection ratio is actually decreasing. So say, you know, this is, you buy LM741 chip, you look at the data sheet and you find this graph over here, and which gives you this, you know, pattern for common mode rejection. And if I ask you which frequency you would operate this LM741, can you guys give me a range for it? Yes, folks.
Somewhere between 0 and 1
Right.
kilohertz.
So it looks like here at this point, this is a good range to operate, right? Okay. because there you have the highest CMRR. After this frequency, your CMRR goes down. Okay, what would that mean? That means after one, say, just for the sake of simplicity, if say this number is 1 kilohertz, okay, if you apply a frequency which is more than 1 kilohertz, this number will start increasing. It won't be suppressed as much as it is suppressed over here at this point. Okay, so you should be knowing these things. And you know, this is a very good interview question. You may be asked about this. What is common mode rejection ratio? You know, or how it is, you know, linked or correlated with frequency. So that could be an interview question for you guys. Okay,